All right, and so along with that way, in what I was saying about a definite integral is not exactly an area, and I distinguished between an actual area as well as a net area. And a definite integral truly is a net area, as in what my explanation was is still being retained here on the board. So in that way, let's get into example 3, where I want to point out a couple of examples where it's clearly set the boundary between a problem where it is to find a net area and a problem where it is to find the actual area, so that you can, it also help into for your experience as in terms of knowing which kind of problem is which. All right, so now let's call that here example 2. And we're starting out this example by having a given function again. And here I'm going to say specifically the function here is a simple function x, f of x equals x, and we have a given interval. So f of x is defined on the interval from -1 to 1. Okay, so that's an interval for us right here. And so question A here of example 2 is simply to ask us to evaluate. Okay, so we want to evaluate the integral on this function f of x, okay, from over the interval from -1 to 1. So we want to take that integral, or another way of saying it, to get used to it, we're going to integrate. All right, so now in the way how it's worded, then we simply are going to treat this problem as a definite integral problem, and that's all it is. Don't worry about area or anything like that, because as I have explained just right before we started getting into this example, then an integral itself on its own is not necessarily an area. So here it is. It's just one integral problem that we're doing, or it's an operation that we're doing on top of this function. And so here we go. Now we've learned about the fundamental theorem of calculus. So this integral can be done easily by, okay, so I'm going to spend a little time rewriting our integral problem. And then so the next step here is to find, according to the fundamental theorem of calculus, we're going to find the antiderivative of that function x. And so antiderivative comes out quite easily for this one. It's going to be a 1/2 x squared. We don't need the plus c throughout our experience on example 1 we've done earlier. And so now the instruction for the next step now is that from where our antiderivative already found here, we are going to, in the next step, substitute the two upper limits and lower limits of our integral problem here into the function. And so in that way, I'm going to proceed to the next step. I'm going to have 1/2 times 1 squared. This is how my antiderivative is evaluated at the upper limit. And then I'm going to subtract. So here we have a 1/2 with the -1 squared here, evaluated it. And that's how we're going to get to our final answer. And so the final answer for this problem is actually a 0. Okay, so as far as a pure definite integral problem, the answer to this integral problem is a 0. Because once again, as I keep highly recommending, do not always tie yourself down to to the fact that an integral has to be an area, because it's not always. And obviously in this problem it's not an area. So how is this consistent with the explanation I delivered before we got into this example? Let me now bring up the graph and the shading so that you can understand. All right, so here we go. Here's the graph. The slanted line here is our famous graph for f of x equals x. So this is that red line right here. And so here we have our interval between -1 and 1. And so this accumulation as the integral right here, the integral we have on the board here represents is represented by the accumulation of two separate areas. There's one area here being below the x-axis, and there's one area here being above the x-axis. So cumulatively, from all the way from -1 to 1, we have two. They looks about exactly equal amount right here in the way how it looks with the graph right here. And so that's the reason why now the negative amount of area here with the positive amount of area, now it consequently results in the total net amount of area being a 0. And that's how it happens in this kind of problem. And so this part 1 of our example. This part A of our example is nothing but just, my point now further is that on one hand we can just simply treat that simply as an integral problem, but in case you do really want to see the problem here, the integral problem as an area problem, then we can understand this 0 value as the net area. So this is the net area. Okay, the net area, of course, between the curve and the x-axis, and from -1 to 1, and that's how we understand about this value right there. Okay, and so, but on the other truth of that answer, it's just simply the answer of another integral problem, another definite integral problem. Okay, and so in that way, the same example here, but let me push that into a different wording. So now I'm going to call that part B. All right, so we want to find how about, I'm going to have to put that in actual wording right here. We want to find the actual area, okay? And so this is commonly how it's being worded. I mean, author of problems out there don't always have to, those authors who write problems out there, they don't always have to indicate that specific, like the actual area versus the net area. So clearly an actual definite integral itself is the net area. But now when it just simply skip the word net area and it's telling you that, hey, find the area, it's intended for the actual area where everything has to be positive. Okay? And so we're going to learn on the go here. And as we try to solve the problem here, I'm going to also introduce a couple of properties here of integrals. So find the area of or how about find the area just simply between the function f of x and the x-axis, okay, and the x-axis, and from x equals -1 to x equals 1. All right, so find the area between the x-axis, the function, the x-axis, anywhere from -1 to 1. Okay. And so now when a problem like this is brought to you, is brought to any of us, we definitely need to see the picture. So in these modern day where calculators and technology resources are all over the web right here, hop onto Desmos, hop onto your TI calculator or your standard graphing calculator to obtain for yourself a quick graph and have an understanding of the graph. And so now again, I'm going to swing back to my Desmos here. So allow me for now to skip out the shading area. So the interval is from -1 to 1 as request. And so the area as a requirement here is indicated to be the area between the x-axis and the graph. So notice how the graph is switching between the negative sign and switch to the positive side above the x-axis here. And that's why it consequently produced the kind of area as we have seen earlier. So in part A, we already understood that the net area here is a 0. Okay, but now if we physically see this as area, as a total area, then we cannot see this as a negative area, but we also must see this as a positive area as well. Okay, so we have to apply a couple of tricks right here. All right, but now at least that's the picture over here. You can pause the video and take a hand sketch version of that, but since I'm pulling that out here right on the computer screen, I'm not going to draw that on the board anymore. Now if we're looking at the graph, apparently we have two different areas here. One area sinks below the x-axis, and that area, supposedly negative here, stays somewhere from -1 to 0. And then the other area above the x-axis, supposedly positive area here, is that area that takes place anywhere from 0 to 1. And so we notice that there's a switching point, 0 between -1 and 1. But so the problem we're doing here strictly wants area. It wants area as the actual area. And that means we have to find a way, even though the graph here shows that our area on this side here is a negative area, but we have to find a way to calculate this as a positive area. And then for this area here, it's already positive, so we're just going to calculate that with the usual integral. So that's a plan right here for doing that. And so now this is what I plan for doing. So as the actual area, we're going to really, for a problem like this, since the way how the graph is broken up into two separate areas, there's a negative side and there's a positive side, we are forced. We have no other choice rather than producing the problem into two separate integrals. One integral accumulates from -1 to 0. Okay? But if we're doing simply like this, it's going to give us a negative answer. Okay? You can verify me that. But now the trick here is that we want that area to be positive. And so I'm going to I'm going to just put a negative sign to that. So that's the trick that I want my students, especially the students for business math, or the students for all of those on track for those social and health sciences major, that anytime your function itself stays below the x-axis, stays negative in the x-axis in a certain interval of integration right here, then you can always do the trick. And this trick is only for when you're doing that kind of problem where you're finding the area. And so now doing this, it will produce a positive area. But now that integral there is only for the area on my picture here from -1 to 0. And that's the way how the integral accumulation was indicating. It was only from -1 to 0. And now, but it's an area, so we need to accumulate with the other piece of the area. So now that other piece of the area can be calculated as an area from 0, as an integral from 0 to 1. But now in this interval of integration, on this interval that we're doing integration work, or we're taking the integral work right here, then the function itself, in the same original way how it's written, has already been positive. So we don't need to apply any treatment. Once again, the whole purpose now is that we need to add it up piece by piece, and we have to break it up so that in every single little piece here, in each of the pieces here, we have to ensure the answer for each piece is a positive value. And that's why sometimes when just simply finding an area problem, it produces more work for us. So this second one here, already we know for sure it's going to produce a positive area. That's one here, we did the trick by putting a negative sign in there. I can also write a negative sign with red ink so that it reminds people about that trick. So anytime we recognize that in an interval that we're taking integral work here, and our function in particular produce a negative result, and if we want to find an area, then we can just always put the negative sign there. And then when we will turn into a positive result, and then summing it all up, it's going to get the total area. Okay, so now once we have had that successful point right here, then we are ready for doing an actual work. But in the end, to the rest of the problem, we're always going to have two separate answers being added together. Okay. All right, so now I am going to swing to my other board. Right there. And so now we know that this separate piece of integral, -1 to 0, and the function is minus x dx. We can get the answer easily by, so it's a negative sign, it's a coefficient. Think of that as a coefficient 1 when you get your antiderivative. So -1/2 times x squared, and then we're gonna need to eventually put in -1, substitute in -1 to 0, and that will give me, so 0 is a higher end for this particular integral problem, so I'm going to substitute that in. So -1/2 times 0 squared, okay, minus, and now that's all that there, and then minus, and now -1/2, okay, times -1 all squared, okay, and so the answer here would give me simply just that area here is a 1/2. So that 1/2 here is about how big the area on this piece right here. You see, I'm putting the grids here in this problem in square units right here, and so that you can see this is 1 unit square for whatever 1 unit's length is. But if this is 1 unit square, and see our area of this rectangle, of this little shape right here as a triangle is a 1/2. It makes perfect sense like that. Okay, so we have already, and this is now really a positive physical area. So now let's find out the area of the other piece, and then we're gonna total it up. Okay, and so now in that way, so my next integral that I have produced from the earlier step, from 0 to 1, but the function now is x dx. And so now it's two separate integral work, as I've been indicating. So positive 1/2 x squared, and then the instruction says we're evaluating from 0 to 1, and now we are going to do so 1/2 times 1 squared, that's capital F at 1, and then I'm going to subtract now 1/2 times 0 squared. Okay, and so the answer here is another 1/2. So we have two separate areas. The second 1/2 I've just found is the other area here, being already itself an area that's above the x-axis. But now the total area we're looking for is going to be the sum of these two. That's piece switched down below the x-axis, and the other piece above the x-axis. Okay, and so now in that way, this total area we're looking at now, in the next step, consequently, the total area we're looking for is going to be 1/2 for the left piece plus another 1/2. So 1/2 here plus with 1/2 there, our final answer is a 1. And that's how we're finding the area, the total area. So it's not a net area for this problem. So we're not going to simply just take one integral. So see, there would be people asking me question, Professor, why don't we just take the one cumulative integral all the way from -1 to 1? You can see, but that's the problem right there. If we simply take one integral, then we're going to end up with a 0 like in part A. But now we purposely want our problem to be an area problem where we have to sum up individual pieces when we have to. And that's the way right there. And the particular thing that we need to pay attention to is that in some pieces, in some intervals, it could be more than one intervals where the interval of integration of taking integral work is producing a negative area. Then we have to put a negative sign in front of your function in that interval so that your final outcome would give you a positive area. We are working with areas now for this particular part B of the example, and that's why we have to go through all this extra steps like that to make sure, to ensure that our final answer is all the proper terms for areas. Okay. All right, so now we are ready for a good application of the integrals here. All right, so let me now introduce. Yes, integral, even though an integral on its own is simply just a calculation work, and it was done, but we can quickly arrive at the answer by relying on the fundamental theorem of calculus. But a lot of places, or the biggest application of integral is to apply integral into, or to bring integrals into finding an area. And you have seen that in a small little example just now. And so, but now, generally speaking, I want to introduce the following area problem. So it's one good problem that's worth our attention to mention. It's an area problem right here. Okay, and so now I'm going to say as following. How about let f of x and g of x, okay, be two functions that are defined and continuous on a given interval from a to b. And of course, satisfying here, let's say satisfying, how about f of x is greater than or equal g of x. Okay, at least on that interval from a to b. Then in that way, if we have these three requirements, the two functions here are continuous and defined, and then the two functions have this inequality. Basically, this, don't get yourself too hung up with this inequality, but the idea is that one function, one curve stays above the other curve. That's what it is. I mean, it could be g here stays above f, but the point now is that one curve stays above the other curve, right there. Okay, and so now, once we've had all that requirements checked, then we're gonna have the following result right here, and it was well proven. Then the area, okay, the area between the two curves f of x and g of x, okay, shaded from x equals a to x equals b, okay. That area, read the description a little carefully, but that area there can be calculated by performing the following integral problem. First, I'm going to produce a function c. So f, if here we recognize, that f is above g, then I'm going to go f minus g. I'm going to take the difference between f and g, but f minus g specifically. Then I'm going to find the integral over it from a to b in respect to x. Okay, so that's how we can find the area, and this really always going to give us the positive answer for the area. Okay, so it's a way of how to find. So this kind of problem that I'm introducing here is called the area problem, but more specifically area between two curves here. Okay, so how about the area problem, but it's between two curves. All right, it's an area between two curves. Yeah. And so quickly, as an explanation of what's going on here on my board. Then allow me to briefly make a sketch on my other board there. That see, we have an interval from a to b, and our two functions are defined on this interval in this window, and being continuous, and one of them is above the other one. So you can call that f is above here. So this is f of x, okay, and g of x is another function that runs down here. This is g of x. And that's what it means by at least inside of this interval from a to b, that our function f is above the other function. Okay, and so in that way, once we are guaranteed with, once we know we are within all of those requirements being satisfied, then see this area being shaded between the upper function and the lower function, and inside of that interval from a to b like that. That's to find that area. This area is see, we call that a. That area can be done by taking the accumulation of all the stripes. See, stripes all over. Long stripes, short stripes. But it's accumulation of all the vertical stripes from a to b. And then we're taking f of x minus g of x, okay, dx. And that's how we're doing it. All right, and that will get us the exact answer. What a fascinating world of application out there when it comes to finding area. All right, so right there in that way, actually I want to leave my other board where I introduced the problem here. So I'm going to still leave this here. Let's quickly erase the other board because the picture here was only to demonstrate the idea, and we will see that all of these are graphing again when we actually bringing it into an example. And so now I'm going to call that example 3. All right, so now in my example 3, so now I'm going to start out just simply having one instruction, find the area. And now I mean really find the actual area, not the net area. Okay, find the area. Okay, and part A of our example here, let's say the area here is between two curves. One of them is f of x equals x squared plus 1. And the other curve is g of x equals 1/2 x. And of course, this area here between the two curves and shaded from x equals 0 to x equals 1. Okay, so at some point we have to have a problem where things are quite worded or things are quite wordy a little bit. Okay, so this is the description of the area that we're trying to find. It's the area, it's between two curves. One of them is the x squared plus 1 function, the curve for x squared plus 1. The other one is the curve for g of x equals 1/2 x. And then the area is further known to be shaded anywhere from x equals 0 on the x-axis to x equals 1. Okay, and so now, before I really tackle it down right there, let me quickly prepare my calculator, my graphing calculator screen right here. And we will have a much better understanding of this. All right. So the graph in red is the graph for the x squared plus 1 function, f of x. So f of x is right here. Okay. And the graph in blue is the graph for 1/2 x. And you can quickly verify me with that. Okay, and so now -1 to 1 is the interval here. And so now I'm going to bring up the shading area. So I had machine doing that, but we can also easily sketch this area on papers and with paper and pencils right here. Okay, so go ahead and you can pause the video if you have to in order to verify for your own sketch if you are working along the way with me right here. But this is the shaded area that satisfies the requirements. We want the area to be between the two curves, f and g. Okay, and from x equals 0 to x equals 1. And just like that, right there is what we have. Okay, it's in between x. And actually, I made a little mistake, but I can easily fix that. Right there. It's not from 0 to. It's not from -1 to 1. It should be from 0 to 1. So that's the picture right there. Okay, so the interval is from 0 to 1. All right, so and I can zoom it in a little more. So now that's my picture right here. This is the shaded area. All right, so it's between. And so now if anyone is having the question for me that, Professor, so how do I decide between the two functions here? How do I decide which one is above and which one is below? Simple answer. Now these functions we're doing are simple enough that can be handled with your graphing device, graphing calculators like the decimal I was doing. So look right there on your decimals. Okay? Look right there on your decimals. And you can also easily sketch this thing, and you can see that graphically speaking, you have your x squared plus 1, at least in this interval, stays above the g of x equals 1/2 x in blue right here. Okay, so that's one way, one solution, if you have technology immediately available for you. So that's one way. But you can also, there's an alternative that you can quickly verify, because see, the description here did not tell us. So back to what I was saying, using a graphical device, a graphing device to decide who's above and who's below inside of this interval is one choice. But in case you don't always have technologies available immediately, then you can also do this. It's another trick right here to help you quickly decide. Pick a value between 0 and 1. Because your main aim, your main interval of the aim here is anywhere from 0 to 1. That's your interval. So pick a value between that. Let's say 1/2 is between that. Okay, so 1/2 is inside of that. And so this sideway curve right here, if in case I haven't mentioned that before, then this sideway curve with a little dash in between, it means 1/2 is a value somewhere in between 0 and 1. So, and that's just a choice I picked. Basically, we pick a point between these two values. And now I'm going to substitute that in. F of 1/2. Find a value for that. So 1/2. Now we can do this with just very basic calculator. We can do a calculation like that. Okay, so that's a 1/4 plus 1. It gives me a 5/4. Okay, now, so g of 1/2. So now g of 1/2, it gives me 1/2 times 1/2, which is a positive 1/4. So now we can compare. 5/4 is obviously greater than 1/4. So now that tells me that at least, I mean, we only chose one point, but it represents the reality about the two functions here inside of that interval. It's a whole generality that can be represented by one chosen point here. Okay, so now that means we know that f of x is above g of x. See, greater than, higher, 5/4 is higher than 1/4 right there. It's a one quick trick, so now I can immediately erase. So now the reason I mentioned this is because, see, we're not only knowing that we need an area here in between these two curves, and from 0 to x equals 1, but we also found out, it's satisfied that one function is above the other one. And in our case here, yes, f of x is above on the g of x. So now in that case, we are ready for setting up our integrals. Because without knowing this requirement, it's impossible to set up it will make it hard to set up your integral correctly. So we need to decide, we need to know who's, and usually no one is telling you that. So you got to be on your own to verify it, between the two functions here, who's the bigger one, who's staying on top, and who falls below the other one, okay, inside of your given interval. So now once you nail down that f of x is greater than, then now we can set up the integral successfully and get our work ready for the real math right here. So the integral now is accumulation from 0 to 1. That's just simply the interval given here. And then our f of x is the upper one, so it's x squared plus 1. That's the f of x. I'm going to subtract the lower function. So high minus the low. That's the general rule right there. So 1/2 x is here. Okay, and then that there, so we take that as one brand new function to take the integral over. And in respect to the x variable, now we have a complete integral setup ready for the later work. Okay, and so now what matters now is we're going to simply take that as a definite integral problem simply from this point on. Okay, and believe me, the answer will come out being an area which is a positive value. So if for any reason for a problem like this, we purposely set it up to be a final area, and you ended up with a negative answer, go back and check your work. Okay, it might sound a little ridiculous. I have to remind anyone this, but at some point when we in a rush situation, we might end up with an answer that we can just accept without any judgment. Okay, so it's just a sign of warning for errors. Okay, so find the antiderivative of the two terms here. So first term is an x squared. It gives me 1/3 x cubed. Okay, that middle term is a constant. How about I'm going to integrate this one first. I'm rearranging the terms a little bit. So now that gives me a 1/4 x squared. And so allow me to assume that anyone at this point has been fluent watching this video. You have been fluent with your skill of taking the antiderivative. And so this comes out as the derivative of that 1/2 x, and the negative sign is from there. Okay, and now plus 1. Now it becomes plus x. And so that's how we got our antiderivative. Now I'm going to substitute in 0 to 1. Okay, I'm going to plug in 0 and 1. So in my next step, really I have a 1/3 with 1 cubed minus a 1/4 times a 1 square plus 1. Okay, and then I'm going to subtract out the other part. 1/3 times 0 cubed minus 1/4 times 0 square plus 0. All right, and so anyone can easily see that all this here is a 0. So we mainly only have to take care of what that value here comes out for us. Okay, and so final answer of mine is going to give me that will be 13 over 12. All right, that amount of area is 13 over 12. Okay, and so that's the area, how big this area that's shaded in this picture described right here. Okay, and so that's how we can apply our understanding into doing an example, and we learn a little bit of experience of how we can decide in an interval given for us in a problem who's above and who's below the other one right there. We can do that either through a graphing device, or we can do that a little bit with the math like that to check. So simply, if we're doing that without the graphing calculator, then simply pick a point, and then substitute that point into your two functions. Whoever is higher value in that interval, then that's the one being above, and whoever is lower value, that's the one falling below the other one. Okay, and so I'm going to get back to the other board, and let's do one more problem. Now I'm going to erase this work right here. And so part A was a nice problem. Nice in the sense that it had a lot indicated for us already. It gave us the two functions, and it gives us the start and the end of the interval, and usually that's the nicest one already. And then now I'm getting anyone viewing this video into a problem that's not as nice, meaning we have to dig out more information out from the problem instead of having everything ready for us, like in part A. So in part B here, let's say we want to find the area. And the wording is quite standard here, enclosed. Okay, find the area enclosed by one of them is f of x equals the minus x squared plus 2. And the other function is g of x equals x. Okay, so have a moment to read and understand the wording of this problem more carefully, and then I'm going to point out. Okay, so the dangerous thing about this problem is that it only gives us the two functions, and that's it. Of course, we know it's our responsibility to decide these two functions, who's above, who's below. But the big missing part that, right at first sight, it almost becomes a threat for anybody. It would almost become a threat for anybody is that it doesn't have the interval given. It doesn't specify where do we start the area from and where do we end the area. We are supposed to find that on our own right here, and that's the way how it's how it's worded like this. It's an area being enclosed by. Okay, and so I'll show you what that means right now through my graphing device. All right, so let me spend a little bit of time preparing my screen right here. Okay, so now let's see what the graphs look like on the computer screen. All right, so there we go. So in your experience with graphs of functions, then you should be well familiar that this parabolic shape is the graph for our minus x squared plus 2. Okay, but then, and this slanted 45 degrees line right here is our graph for the famous function g of x equals x. So now the one in blue here is clearly for g of x, and the one in The one in red here is clearly for the f of x. Okay, so what does that mean by the area enclosed? Okay, let me hit back to that board and point out the wording. So what does that mean by find the area enclosed by these two curves? This is what it means right here. Enclosed means the amount of area that's totally trapped inside. Totally trapped inside. So see right there with the picture. So one curve goes like this and the other curve goes like that. So if we're looking at this area, that's not enclosed. Because this area here, then it has all that floating out. Okay, there's no trapping on the right end of that. So that's not the area we designated. We're looking for. How about this area down here? That's not enclosed. And how about this area that's not enclosed? The area we're looking at, the wording say enclosed. That means completely be trapped in and having only these graphs being the boundaries that sets enclosure of that area. So ladies and gentlemen, the area that we're looking at is actually here. That area that I'm now shading it. Okay? So that's the area that I'm shading it. And so the challenge for this area, see right now on the computer screen we have the nice graphing calculator, the decimal, so it comes easily that you can see. Now we can see that the enclosed area here, horizontally speaking, it starts at x equals -2 on the x-axis here, right? And then it switch over to, and it ends at this x equals 1 right here. Okay? And so in that way we can easily come up with our integration or our interval for integration. But what if we do not have? What if we do not have the nice calculator, and we sometimes, like I said, many times the technologies are not immediately available. Okay, technologies are not immediately available. So how can we find the two the two crossing points like this, where it becomes our left end of the area and our right end of the area? So here's the math for that. To find, so here, besides deciding who's above and who's below the other one, we also need to find the left and the right end of our enclosed area. And so to do that, I'm going to set the two functions equal to each other. F of x equals g of x. That's what we want to do. We set f of x equals g of x. That will produce for us an equation minus x squared plus 2 equals x. Okay, so we have an equation, and so now we're back to some algebra work. I'm gonna bring all the non-zero terms. I'm gonna bring all terms to one side. So minus x squared minus x plus 2 equals 0. Now I realize for myself I have a quadratic, and then solving this quadratic, I can cancel both sides by -1 first to bring that into a positive leading term quadratic. Okay, and then from here you can either use the quadratic formula or the factoring method. It's just me that for this problem, I see factoring is a little faster for me. So this is x plus 2, x minus 1, okay, equals 0. So we consequently end up with two values. One of them is x equals -2, and the other one is x equals 1 after we solve that equation. And so this result here agrees exactly with whatever it shows on our graphing screen right here. Okay, so on our graphing screen, see the two graphs crosses right at x equals -2. And see, so now I use that term where the two graphs cross, because that's where it is. That's what happened. When the two graphs cross, that's where it traps the area enclosed in between them. Okay, and so x equals -2 is the left end where the two graphs first cross, and then x equals 1, the other value that we have solved for algebraically, that's the right end where the two graphs cross. And so now we know that our interval for integration work is anywhere from -2 to 1. The solving work does not tell you the order, but now once you have done solving, then it's obviously clear that -2 is on the left and positive 1 is on the right. And so now we know that our integral setup has to be the following. As the integral setup goes from -2 to 1. Okay, that's left end, that's right end, or that's low end, that's high end. Okay, And now between the two functions, who's above, who's on top? I mean, you have seen that through the graph, so it's easy to see that f of x is, and at least in this interval, f of x is above g of x. That's what we saw through the graphs. Okay, so minus x squared plus 2, and then minus x. Okay, because f is above, g is below. So above minus below, or upper minus lower. And then we're producing that integral work like that. And that gets us the area that I call A. But then, once again, in case that you don't have technology immediately available for you, then after you solve for your two values here as your integral, as your interval boundaries, then you can also pick a point, see? Between -2 and 1, 0 is clearly being inside between -2 and 1. Okay, and so just like the work I've done in part A, we can quickly substitute 0 into f of x. That gives me -0 squared plus 2, which is equal to. Okay, and then the g of 0 equals, see, g of x is defined as g of x equals x, so equals 0. So now obviously f of x is a higher value than g of x when x equals 0, a value that's generally inside that interval from -2 to 1. And so 1 point is enough to represent the generality of the whole interval. So at least I know in that interval, algebraically, this function f has to be above, has to be the upper function compared to the g of x function. Okay, so you got two different methods of deciding who's above and who's below. And so now I came to that final setup. Is all due to that method that I have introduced here. Anytime that we recognize whoever is above the other one, right? One function is above the other one in that designated interval, then we have to set up the integral in a way that the one that falls, say, above, subtract the one that stays below, right? And create the integral, and then start doing the integral work for that, the definite integral work. All right, so now the integral work comes out easy from this point. And I need to write things a little closer to make space for myself here. All right, so now what it gives me here is minus 1/3 x cubed. I'm going to hold on to that constant term. I'm going to take the antiderivative here, so minus 1/2 x squared, and now I'm going to plus 2x. We don't need the c, but then eventually with this antiderivative, I'm going to substitute in low for -2 and high for +1. And so now I can do the calculation, proceed with the calculation. So -1/3 times 1 cubed minus 1/2 times 1 squared plus 2 times 1. All this here is capital F at 1. And then I'm going to subtract, and now I'm going to reproduce the whole thing here, but substitute it in, evaluate it at x equals -2. So -1/3 times -2 all cubed minus 1/2 times -2 squared plus 2 times -2. Okay, that's a -2 right here in case it's hard to read for anyone. Okay, and so all right, so my final calculation in fraction is area equals 9/2. That's our final answer for that kind of problem. All right, and so that's the end of this example 3. So now before I'm completely done with this particular lecture about definite integral, because again, and this video lecture, as I said in the beginning, is intended for the students who are on track for business major and or the social and health sciences majors. And so after this example, I am going to, if you keep checking back with my course, I am going to keep posting as many examples of applications of why area problems so matter in your field right there. Okay, so for example, if you are on track for, if you are taking a class for as a business calculus course with me, then you check back with my course where I will post a video on specific examples about why you need to find areas in your business application, or for health scientists, or for social social scientists out there, if you take a class with me, with a math course with me for those majors, you can always check back with your course. Even after your academic term is over, you can always check back for more the application problems like that to see why area problems are so important in your field. Okay, and so now, before we completely move out of this lecture, now I want to produce this little problem here as an FYT for anyone. Okay, so we can take this problem as an FYT for your trying. Okay, and the function here is simply x squared, and I want you to find for me to calculate, to evaluate. There are so many ways you can say it now. Evaluate the definite integral from 0 to 1 on this function right here for me. Okay, it's a definite integral from 0 to 1. But now you have learned the solid fundamental theorem of calculus. I want you, in this FYT for your own trying right here, I want you to give it a try and come up with your own answer. I will just wait here for your resume. After you resume the video here, supposedly you're gonna pause the video and try it on your own. And after you resume, I'm only gonna say the answer. And then we're going to talk a little bit more about that answer and see how it all coming consistent with what we have done earlier. All right, so now, assuming you already had some work right here, now I'm just going to tell you the answer without any steps. The answer here is a 1/3. The answer here is a 1/3, or in decimal, it's a 0.3333. Okay, and then, so, what is the meaning of this? All right, so this picture looks just so familiar. It was that very first picture when I picture when I brought up and introduced the concept of Riemann sums. But so now, somewhere throughout our discussion about the Riemann sum, and I was expressing that I knew at that time, I was saying in my video lecture there that I knew the answer for this area was 1/3. And so just now, what is the meaning of our answer we have just found there? The answer we have just found here, and see now this particular integral, it's not only an integral, it's an actual area, because the piece of area right there in the picture you just saw earlier is a positive and just fine area. So this thing is perfectly, the answer for this integral is perfectly the area equal to the area we found there. And so we use the integral here to find the exact area, and so that area is a 1/3 right there. And so that's how I knew it. So back in the days of doing the Riemann sums, and I knew that we had a target, knowing that our area needs to be 1/3, so that we know whether we're still above the area with the Riemann sum approximation or still below the actual area by using the Riemann sum approximation. But then another further understanding that I want to point out, see, 1/3, but 1/3 of what? 1/3 of what? So this is the shaded area, but 1/3, because see, when we're now starting to get pretty far into the theoretical side of mathematics, then usually units are skipped. Okay, so now it's saying that area, yeah, that shaded area here is 1/3, but 1/3 of what? So now think about this. On standard, 1/3 of whatever area value, it's to be relative to 1 unit square. So on your graph right here, you see I'm trying to trace my mouse cursor right around this unit square right here. Okay, so what it says here is, see, this unit square has area 1, because 1 on the x-axis, 1 on the y-axis, it gives me an area 1. So this area being shaded in pink color right here it does look about 1/3 of the whole total square right here. And that's what the meaning of this answer is. And we have done that, and you have now found that answer. It took a little bit of about a few lectures, but in the end we arrived at that, and we found a beautiful way to obtain the exact answer on, for area kind of problem on very irregular shape. Okay. And now, one more thing that I need to mention. And so now, if you look back into the lectures I gone over about antiderivatives, and at some point I said I informally allowed you to see you got a function, and I informally introduced the symbols right there, okay, and as an instruction for indicating that we want the antiderivative of this. So the answer at the end here was an antiderivative. And then, of course, finding an antiderivative, we do the add c thing and we do the plus c thing. And then at the end of that lecture there, if I remember correctly, I informally introduced that this whole symbol is called, the whole problem is being regarded as the indefinite integral. Okay? And so now, it's now time to make that real good connection here of why we call it indefinite integral. Because now what we just now learned is we got a function. And see, we got that symbol, similar symbol here. And then we got the dx thingy, okay? And then we got the low end and high end. This is definite. The one we're looking at here is called definite integral. That's what I've been saying throughout the whole lecture here. This thing right here is definite integral because it has the definites low end and high end. So now if we're looking back at what we've learned earlier, now see the reason I call it indefinite because it's the exact pretty much same work, and it's really half of the work. It came straight out as a consequence of knowing the fundamental theorem of calculus. The big part of doing this is to find the antiderivative. And so that's why now we can legally go back and say, hey, so we can now call this thing only just to introduce that that we're taking antiderivative, but because antiderivative is so important in the work of finding definite integral, so now just a work finding antiderivative. Now we can legally and formally say that this here is being called indefinite integral, versus as the opposite way of being a definite integral. Okay, and so indefinite integral. So what we had here, what we've seen earlier, is called indefinite integral. Now you know why we're calling it like that precisely. Okay, indefinite integral. And so indefinite integral, we expect our final answer to be a function. And then definite integral, I expect my answer here to be numerical, some kind of value. Okay, some kind of final value. It could be negative, it could be positive, it could be zero, but it has to be a numerical value, whereas here the answer needs to be a function, another function. And so now, needless to say, you have already noticed that throughout my lecture here, you see when I see the dx right here, it's an indicator that, see, if your problem you're doing is an indefinite integral, then it's an indicator that you find your final antiderivative as treating x as the main variable. And so it's similar the same way that is. So now when I see the dx right here in my definite integral, I know that I'm taking the derivative, the antiderivative part of that, but treating x as the main variable. Okay, so your antiderivative must come out in terms of the x variable, and then these variables are all in terms of the x, or all in respect to the x variables, because it's indicated here. So it's an indication. It's an indication that x is the main variable. Okay, and so that's what I'm trying to express. Even though we will never have to, for our kind of class here, our kind of course here that we're learning, we don't even have to go too far into the theoretical details of that. But I'm just feeling insecure if I don't mention this piece of information. That's all.